Hello, my name is Rob Armstrong. I'm with the CUDA Toolkit team here at NVIDIA. I'm here today with some of my colleagues, Rob Nerdney and Arthi Sundaram, to tell you some more about the exciting new features that we have coming in CUDA Toolkit 12.2. Now, before we get in, let me set the stage a little bit for where we are in the release cycle. Many of you probably know that CUDA Toolkit has a new release about once every quarter. These new releases, which currently are part of the 12.0 release cycle, introduce new features and new functionality for existing GPU families across the board, not just for our latest Hopper and Ada Lovelace families. Every other release comes alongside what we call an enterprise qualified driver. These are drivers that go through extended QA cycles and have longer support lifespans and are suitable for release and use in data center environments. The current driver release, corresponding to 12.2, is R535. R535 is a long-term support branch, which means that it will be fully supported by NVIDIA for a 3-year life cycle. Now, with that, let's jump into a little bit about what's new prior to 12.2, just in case you might have missed it. Of course, when we introduce a new CUDA major version, it comes along with a lot of great new GPU architectures, and that includes, this time, Ada Lovelace with support for L40, L4, and more, and the Hopper series GPUs, in particular H100. We have Grace and Grace Hopper coming a little bit later in the year. And with our new major version at CUDA 12, we reset our minor version compatibility guarantees. My colleague Rob Nerdney will talk a little bit more about that later in the presentation. But ultimately what that means is that with any driver newer than R525, you can use CUDA 12, CUDA 12.1, CUDA 12.2, and so on, without having to worry too much about the alignment between the driver and the toolkit. I mentioned lazy loading last time, if you had seen our last release video, and really this has been going on since CUDA 11.7, but over time we've made incremental improvements in how we can introduce lazy loading. We make some very drastic reductions in binary load time. We're able to minimize host and device memory usage by only loading not only kernels, but also functions from the libraries as they're used. It's been enabled since CUDA 11.8 as an opt-in technology, and we're actually defaulting to having that enabled for everyone in CUDA 12.2, which we're very excited about. I'll talk a little bit more about that later on. We've also seen quite a few improvements to graphs and just memory management enhancements in general. We've seen pretty dramatic improvements and updates to CUDA dynamic parallelism and graphs, both on the capture and execution side. We've significantly reduced the latency for launch overheads. We've added all new kinds of graph launches, including tail device launch, sibling launch, and more. So if you're not familiar with CUDA graphs and how they can benefit your applications, definitely check out the videos from GTC from my colleagues Stephen Jones and others, and refer to some of the earlier YouTube videos that we've had on CUDA releases, because CUDA graphs are a really great way to minimize launch overhead, especially if you have a lot of small kernels, which is of course common in the machine learning space. We also have a huge number of memory management improvements that we've put into place, not only for Grace Hopper, but for all of our GPU families on the desktop and beyond. I'll talk about one very significant one that we're introducing in CUDA 12.2 in just a second. But if you haven't seen it already and you want more information on any of these topics, I do recommend that you go back and check out our video from a few months ago on the release of CUDA 12.0. It goes through a lot of the changes that went into play with the major version boundary and introduces a lot of the new functionality that you can find in both Ada Lovelace and Hopper GPUs. So I'll assume you've taken a look at that. If you haven't, please go check it out. But for now, let's dive into some of the cool new features that have come with CUDA 12.2. Now, I'll start with a feature that you may be familiar with from just computer science courses and background, or from seeing it in the Linux kernel. It's something called heterogeneous memory management. And what that is a kind of unified memory that works with all kinds of allocators. Now, unified memory, if you're not familiar with it, is not new. It's been around for a long time. We introduced APIs, roughly, I would say 6 or 7 years ago, CUDA malloc managed, CUDA free, and so on, that allow you to take memory and allocate it. You can do prefetching and move it around in the system. But ultimately, if you had allocated memory through CUDA malloc managed, you were able to kind of, in a sense, forget about it. If you needed to have it available on the GPU, the system would automatically transfer it to the GPU. Similarly, if you had memory that was resident on the GPU and the CPU needed access to it, the CPU could go and fetch it from the GPU, again, without your application needing to really know about it or pay too much attention to it. Now, those of you who have worked with it know that it comes with a little bit of an asterisk. Of course, if you're waiting for the system to access memory and it has to migrate it from someplace far away, that can come with a performance trade-off. And so you may want to do some prefetching or allocations and things like that. But at a high level, conceptually, this is sort of a fire and forget memory system. Now, what happens is that as we move into heterogeneous memory support, or rather I should say, as we move into heterogeneous memory management, we now no longer have to work with memory that's specifically been allocated through CUDA malloc managed. And so that gives us support for memory that's allocated through pretty much anywhere. You can have it allocated through malloc and new, you can mmap it, it can be on the program stack. Basically, all of your program's memory is now available to the GPU. And it sets us up for a lot of really great programming model enhancements. Of course, when you have really tightly coupled memory between the host and the CPU, or excuse me, the host and the GPU, like you find in Grace Hopper, that enables some really awesome optimizations. But even on traditional PCI desktop topologies, you can enable the entire standard of C++. There's a very long tail of other programming languages, other libraries and frameworks, and things like that. And where this becomes important, I'll show you in a second. Let's take a quick look at what a CUDA UVM program looks like. Before, if you were on the CPU, you might have some algorithm that looks like this. And don't really pay too much attention to what this algorithm is. I'm really just trying to show you a delta between using UVM and using just normal memory on the CPU. So we start off, and on the left side, we're just calling malloc to allocate our data array. We call a couple of functions on it, we use the data, and then we free it. On the right, if we wanted to do the same thing in CUDA with UVM, we would replace the call to malloc with a call to CUDA malloc managed. We would take some or all of the functions and migrate them onto the GPU, run them. At the end, we would call CUDA device synchronize, of course, to make sure that the GPU was done running that section of the application. And then at the end, instead of calling free, we would call CUDA free. Now, with HMM, you'll see that we're sort of back where we started. We can take our early application, which just uses malloc. We can take the subset of the application, in this case, our qsort function, migrate it onto the GPU, add in CUDA device synchronized, and then just free the data as we normally would. And what this really means is that now we're using the same application flow, the same algorithm. We can take that code and with very minimal changes, migrate it onto the GPU and start taking advantage of the acceleration. And you might be looking at this and thinking, okay, well, this is a trivial example. It's ultimately not very interesting, right? I've got one alloc and one free, and it's not really that much work to, change malloc to CUDA malloc managed and all that. So what does HMM really buy me? Why is HMM interesting? And it becomes interesting because applications are not this kind of trivial function, right? Applications are very large. They're very complex. There are many large frameworks and libraries that do their own allocations. You might be making copies of buffers. You might be doing all kinds of things. And what this means is that now we can take applications that are not written with heterogeneous computing in mind and take the memory that's used by those applications, share it with the GPU, and do it in a way that we don't have to worry about interoperability with, these huge ancient frameworks that you might be inheriting in your application. And I say huge ancient frameworks kind of tongue-in-cheek, but it's really a stand-in for anything that you might have in your application that has a cost that's really too high to go through and rewrite it and double-check all of the memory management and so on. If we just want to take a subset of the application and put it onto the GPU as easily as possible, HMM is by far the easiest way to do that. Now, this is an early release of HMM. It's the first release where we've had HMM support, and so some limitations do apply. You can take a look at the release notes for CUDA 12.2 and the R535 driver for the full set of information. But in a nutshell, HMM today is only supported on Linux, and it does require a pretty recent kernel. And I say pretty recent not in an abstract sense. but in a very real sense. If you're in the 6.1 branch, you need to be on a kernel that's newer than 6.1.24. If you're in the 6.2 branch, you need to be newer than 6.2.11 or anything in 6.3. Now, there are distributions that support HMM today. They have a recent kernel version, they have patches and so on applied. But you do have to make sure that you're on, for example, the latest version of the kernel from your vendor. You do have to make sure that you're on a very recent distribution release and so on. HMM also requires the use of NVIDIA's GPU open kernel modules. You may be aware that we introduced GPU open kernel modules sometime roughly, I think, 1.5 to 2 years back as an open source variant of the NVIDIA GPU driver. And it's not the default if you install through the package manager or if you install through the run file. And so you do need to make sure that you opt into the correct version of the driver to be able to make use of it. So we require a modern kernel and we require the open source driver. I've got some placeholders here for example package names that you can install through Debian and RPM. You would replace the XXX with the driver version, in this case 535. For full information about how to do this, please refer to the CUDA installation documents. It walks you through how to opt into the open kernel modules. It walks you through how to switch between the open kernel modules and the legacy drivers and so on. So just keep in mind, if you want to use HMM in your application, at runtime, you have to have both a recent kernel and GPU open kernel modules installed. So this is still a very cutting edge technology for use with GPUs that does require some special thought ahead of time. I would also highlight that HMM right now is only initially supported on x86 CPUs. Now, we expect that to change very rapidly with the introduction of Grace Hopper and so on. But for now, as of this moment in time, at the time of the CUDA 12.2 release, we are supporting HMM only on x86 CPUs. So do keep that in mind. But if you have this combination of things, and if you're interested in trying it out, kicking the tires and evaluating it, we think this is a really game-changing technology, and we're very excited about it. So please do try it out and let us know what you think about it. Now, circling back to lazy loading, I mentioned this earlier on. Lazy loading is something that we've been talking about for a long time. We introduced it in CUDA 11.7 with lazy kernel loading, which only loads the kernels that you use onto the GPU and saves a huge amount of GPU memory. In CUDA 11.8, we augmented it, and we started using lazy module loading. Lazy module loading only loads the functions out of the modules at the time that they're needed, and so we can see some very significant reductions in host memory. And this is something that we've been using internally for quite a while. It's been opt-in until now. We've had it turned on by default in our deep learning containers and in many other containers that are published by NVIDIA. But in CUDA 12.2, this is the first release where we actually have it on by default everywhere. Now, everywhere comes with a little bit of an asterisk. It's on by default in Linux, and Windows will come in an upcoming CUDA release. But for now, as of CUDA 12.2, it's on by default in Linux, and you can try it for your application. You should see, if you weren't using it before, some pretty major reductions in memory usage on your GPU and in your host system from the lazy loading feature. If for any reason you want to opt out of it, you can use the same environment variable that you used to opt into it before, CUDA module loading, but instead of setting it to lazy, set it to the value of eager prior to launching your application, and you'll get the behavior that you've had up until today. We've also made some really important enhancements to how we share GPUs with our GPU multiprocess service. And that is through the addition of per-client priorities into the system. So you can imagine a scenario where you have two applications. Both were written with the assumption that they were the only process running on that system. They're both running at the same priority. But now, in a real deployment environment, you, as the person orchestrating that system, want, for example, application A to run at a higher priority than application B. We don't have priority preemptive scheduling or anything like that. This isn't hard real-time scheduling. These aren't, you don't really have to think about things like priority starvation or anything else. But as a general hint to the system, we can now specify higher or lower priority for a given application. So it's a coarse-grained prioritization between effectively normal priority and below normal priority. And the way that you control that is with the CUDA MPS client priority environment variable. You can set that prior to running your application. If it's unset, or if you set it to 0, your application will run at a normal priority level. If it's set to 1, which equates to below normal, your application will run with a lower than normal priority. And this could be a background job or something that you want to process data continually, but you want to be able to interrupt it or sit on top of it, if you like, with a more high priority application. So again, this is not real-time scheduling. We're not going to preempt an application and kick it off the GPU or anything like that. But when the runtime is looking for what to run next, we'll pick from the normal priority application kernels first before picking from the lower priority kernels. Now, a quick note on our OS support matrix. On the Windows side, this really has not changed. We support all currently supported versions of Windows from Microsoft. I will note the same thing I noted last time, which is that Windows Server 2016 reached its end of life in January 22. So CUDA 12 was the final release that supported that version. And do be aware that support for Windows Server 2019 will continue from NVIDIA until Windows Server 2019 becomes end of life in January 2024. At that time, we'll move on, as will the rest of the world. So just be aware, if you're on Windows Server 2019, NVIDIA is looking at approximately the January 2024 timeframe as our sunset for the overall support. On the Linux side, things look very similar. We are, as always, updating to the most recent versions of these releases from the OS vendors. So on the Debian side, we're looking at moving towards Debian 11.7. Red Hat Enterprise, we're migrating to 8.8 as well as 9.2. Ubuntu moves to 20.4.6 LTS. Rocky Linux 8.8 and 9.2. And then Keylin OS remains the same at V10 SP2. As an additional note here, Ubuntu 18.4 released its last version and went EOL in April 2023. And as such, CUDA 12.1 was the final supporting release. So there is no official support for Ubuntu 18.4 LTS in this CUDA 12.2 release. On the developer tools side, we have some pretty interesting enhancements to our Insight Compute and associated developer tools. In Insight Compute, we have source page guidance that's come online. And what that does is give you the ability to quickly jump around and go to the targets of branch instructions and explore your code. We also give you rules markers, so you can have automated analyses done. We can output source rules or suggestions per line of source. And so that lets you really quickly detect and navigate to the lines in your application that really matter to your application performance. It also has, in the same context, explanations of the detected issues. So we'll be able to quickly jump to the line of source, see what's happening, and then we'll also be able to give you an explanation of any issues or potential issues that we're detecting in your code. Similarly, in Insight Compute, we've added the ability to calculate the potential speedups of optimizations. And so if we're detecting issues in your code, or if we're detecting issues in your kernels at runtime, we'll be able to estimate ahead of time what, following the suggestions, will be able to improve in terms of your overall throughput. And so you can sort kernels based on how much we think we'll be able to speed them up. It helps you understand where you can focus your effort and where you'll see potential benefits. And you can see, looking at the graphic, this is a screenshot out of the tool at the bottom of the screen here. We have a couple of issues that we see in a highlighted kernel, and we're estimating how much that kernel could be improved by following the suggestions that we're giving in the instructions. So this is a really powerful tool, especially if you're newer to GPU optimization. We give you a much better visibility and kind of a more intuitive understanding of how these things come together and how you optimize these applications. But I think the real star of the show here for the CUDA 12.2 release is our CUDA Confidential Compute Early Access. And for that, let me hand it over to my colleague, Rob Nertney, to walk you through how that works and some of the great things that are coming online there.
Hello, everybody. My name is Rob Nertney, and I am a product manager on the CUDA team here, and I am excited to tell you about our early access for confidential compute coming in 12.2. You might have heard about it at our GTC talks, where we went over some of the deep dive technical details as to what confidential computing is, how the nuts and bolts of it work, the details of the security models, the developer considerations as to what you as a developer need to know for APIs, and other things. We will be putting a link for that at the end of this presentation. I highly encourage all of you to go check that out. However, for the CUDA 12.2 release video, I am going to give us a high-level overview for those who are just watching for the first time, going over what it is, why it's helpful, and how you as a developer can start to use it. So before we get into it too far as to what this EA is, we should go over what the confidential compute is trying to solve. Now, historically, we've been able to protect our data at rest and data in transit. This would be commonly known as your hard drives, trying to keep them encrypted or having redundancy in the hard drives to make sure bit flips don't corrupt your data. We have the ability on our data in transit to secure the wires, so to speak, meaning IPsec and MACsec, or up to the application level, things like TLS. Now, data in use, when actually operating on it, whether you're using a CPU or GPU, has had this gap where you haven't been able to secure, both either via encryption or authentication, the data that you're processing at the time. So confidential computing comes in and is trying to build this holistic model as solving the problem where while you are using your data, it remains secure. Now for this, we'll go into some of those details, but the thing to take away from this first one is this is not NVIDIA just coming at it and doing our own style of confidential computing or what we think is best. We are a member of a whole, and this is the confidential computing consortium at the bottom. You can see here that we've got very powerful members, both from the software cloud providers and the silicon providers as well, coming together to make architectural changes, whether that be in the semiconductor itself or from the paradigm of how the software developers handle it. We're all coming together to come up with a solution that enables you, the end developer, true privacy, trust, and security in your data when it's being processed. So what does confidential computing look like when using a GPU? Now on the left here, we have an image which is traditionally what people expect when using a GPU in a hypervisor / virtual machine environment. The hypervisor will have, configured the virtual machine. It will have applied the features that it needs, the RAM, the cores, and it will have attached a GPU to that virtual machine such that it can have access to it. Now, while the virtual machine can't necessarily break out of where it's at, the hypervisor can break in. It has full access to the page tables and can really go in and poke around in the virtual machine's memory or directly into the GPU if it's so desired. Now, CPUs have gone ahead and started to put in silicon features to try and help prevent this, whether they be secured nested pages from AMD or secured TLBs on Intel side. The thing that was missing has been bringing that security to the GPU, because the GPU is still very valuable where it is required to handle these massive workloads, things like LLM AI training, or high-performance computing, or government analysis. We want to try and bring the GPU into this confidential computing fold. So what that looks like on the right here is, of course, bringing in a trusted execution environment, the TEE, where this confidential VM, leveraging the CPU-based security features, uses our standard NVIDIA driver and will attach to the NVIDIA H100 GPU while it's configured in confidential mode. In this mode, you'll start to see, and we'll go over some of those details, how the hypervisor will no longer have access to either the virtual machine itself or the GPU and the data that is being transferred between it. Now with confidential compute, there are three key market uses that we see here. And you can see this tagline, data is power. So in today's day and age, the user data is considered its own form of currency. And what we see is, with this first one here, data privacy and security, there are regulatory regimes, things like GDPR in Europe, HIPAA in the United States, where there are certain levels of requirements that are placed upon the companies where they must provide a certain level of security on user data. confidential compute, having encryption and authentication for tamper resistance, helps give that layer of security, passing the checks such that you can use this data even within the regulatory requirements. Second big option here is how the system owner operators can actually reduce their liability. If they were to have a bad actor with some sort of administrative access deciding to go malicious and try and compromise the data or steal and take that data out. The second big one is digital asset protection. Now in this one we have two again. First is hardware-based security features, where this silicon-based encryption standards will help enable deployment at the edge, where you might not necessarily be allowed to use sensitive data processing. You might want to, because that's the big idea of edge computing these days, but just due to various reasons, you haven't found that it was secure enough. Having this security of confidentiality and integrity with confidential computing should help many new markets open up their ability to operate in new areas. Second one is ISVs and model creators here. Now, they might be building the top new model. They might have data sets that they have that is their proprietary secret sauce. And they want to make sure that while they might trust you as the end user or the end developer using it, they might want to have an extra layer of security where they ensure that you can only run their application within a confidential computing system. And so confidential computing, we will provide those flags such that they will be able to tell whether or not their kernel is running on a confidential VM or not. The third one here is data-centric trust enables new collaboration. Now, things like federated learning is really kind of interesting, where you're able to take the ability of, let's say, many medical records, and again, with HIPAA restrictions on it, and be able to distribute the learning out such that you don't need to operate on or transfer any of the secure end user data. With this, you're able to now leverage this private data, but still maintain and be able to access some sort of learning from it so you can use it. And secondly, we have internal groups. There are groups, whether in governmental agencies or even within places like financial industries, where they might work for the same company, but they actually cannot be using the same hardware or the same systems due to, again, regulatory or security restrictions. So what this slide does is it kind of goes over the threats and mitigations in a lot more detail. However, what the takeaway is the differences between our early access and our general access. Now you'll see here that we have a bunch of yellow checkboxes in the early access, and those are primarily involved with things that we either know still have some closure to have before our general access, or we're still in the process of performing our security reviews. We do believe that this early access is ready for users to begin migrating their code over and working on seeing how it looks, getting used to the flow, and doing some overall performance benchmarks. However, during the early access, we will also be recommending that you do not put any mission critical or mission secure code or data into the system if you do not trust the system any more than you would normally trust an H100 in the system that you're working on. Now, there will be a white paper that will be going over these threats and mitigations in the full gory detail, and it'll go over what these mean if you care to read about it when it is released. So what this slide is taking a look at here is also giving you a little bit of information, letting you know that the topology configuration options remain kind of the same as a traditional virtual machine with GPUs. In here you can see a system with a GPU without confidential computing mode on. You see one with confidential computing, and you see another third virtual machine with 2 GPUs for perhaps a training-based workload. The idea here is that the virtual machines are required in confidential computing mode primarily because of the way that the consortium has standardized on leveraging the CPU usages to ensure that the hypervisor can't just poke into the virtual machine itself. With this, the data will be encrypted across the PCI Express bus, and if you are in a multi-GPU scenario with NVLink configured, the NVLink will also be encrypted. If you wanted to take one more double click here just to take a look at how the virtual machines will be separated here, what you'll start to see is that since users have this sensitive data, we need a method to transfer data out of that secure memory pages inside of a virtual machine into the GPU itself. So in this case, we have virtual machine 1 sitting with the CUDA drivers installed and running and talking to the GPU on the far right. The other two virtual machines in the hypervisor will not have GPUs attached here. You can see that a security processor hardened in this situation, an AMD SEV-SMP GPU, handles all of the memory paging, encryption, and authentication on its own. So all those keys are handled outside of the scope of NVIDIA. Now we're able to store our private key and allow a small gray box here of unprotected memory such that we can put in our data payloads. So what happens here is your application will automatically and transparently be converted into a path in which it will be encrypted and signed, and then transferred over to the GPU via this bounce buffer, as we call it. So the idea here is that the DMAs can access the gray area with the green lock in it, perform the transfer, and then it will also have the key on its end after creating a secure session to do the decryption and authentication and then work on that payload. Some of the collateral and ancillary software that's coming with confidential compute is going to be the attestation software stack. This particular stack is going to be a provided open source application that will let you test and challenge the GPU to ensure that A, it is a valid NVIDIA GPU running valid, up-to-date, and non-revoked firmware. It allows you to check the validity and revocation status of the driver that's being put into the system as well. After reading this, it will also provide measurements, both static and dynamic, of the GPU itself, and will provide all of that with a signature that you can then locally attest to or locally verify to a set of golden measurements, which we will also be publishing online. With this, we will also, and this will be our primary recommended flow, be providing a remote attestation service. This service will allow you to send your signed copy of the evidence into the cloud, such that we will be able to check the status of the revocation of the hardware, the firmware, the driver, validate that it came from you and your virtual machine, provide our checks on our end, and then provide back a token that is also, of course, signed. And then on your system back in the VM, you can be assured that with the most up-to-date information, whether or not your GPU and the system itself are running the firmware and software drivers required. Of course, with this, should you be running a system that has revoked software or a revoked driver, we will not tell you you can't run. Of course, the relying party being you, you can decide whether or not the risk is worth taking depending on what the failure was. And of course, we will tell you what those were. Now, this particular slide goes over the security standards of which we are adhering to. So, of course, we are currently in the process of getting the FIPS 140-3 certificate. For the identification of the chips itself, you can see the X509, how we ended up deriving our private key on the device, how the session keys are standardized to the SPDM standard. Once again, in the white paper, we will have much more detail as to about what these are, how they're used, and why they are important to you as a user in a confidential computing environment. Now, a lot of times we get the question of, okay, this confidential computing, it sounds really interesting, but am I going to have to change the way I run my code? Do I need to change my stacks? Do I need to change fundamentally an application that might already be compiled and operating today? And the answer is we worked really hard to ensure that this transition would be as transparent as possible, right? So due to that architecture and the CPUs and how they handle trusted execution environments, there are going to be a few areas where changes are required. Primarily, it comes down from the fact that the CPUs have put in all this extra hardware to ensure that an unauthorized actor cannot access memory inside your virtual machine. Now, those of us who are familiar with the way that accelerators like GPUs work, you basically set up your payload into memory, CPU memory, and then you tell the GPU's data mover or the copy engine to go and fetch it, operate on it, and write it back. So the confidential computing standards of SEV, SMP from AMD or Intel TDX really kind of stops that. It prevents it by design. So because of this, whenever we need to use kind of pinned host memory or use something where we would do expectations of the GPU knowing exactly where it's going into a virtual machine's memory, those will no longer be allowed. And this, if you have more questions, is in detail in the GTC talk, also by me, Rob Nertney, going over exactly what those APIs are. They are very few and far between, and you can go and see how your application will work. Or once we come out with 12.2 Update 1, you'll be able to just go ahead and drop your code in and give it a try, see how it works. A couple of the other things that are on here is that because the trusted execution environment is being built between the CPU and the GPU only, RDMA applications like GPU Direct won't be accessible. And that's primarily, again, because they just can't access, due to the CPU restrictions, the memory to go ahead and do the DMAs into that. Good coding practices, of course, will always be able to check before doing a forbidden API call. We have done our side with proper error return codes. So if you end up using an API that's not supported, it will have a code that you will be able to look up and end up searching to find that, oh, this was one of those APIs that can't be used in confidential computing mode. And finally, due to the fact that the H100's confidential computing mode is primarily targeting compute workloads, the graphics interop features of some of the APIs that we have will not be supported as well. Developer tools are very important, whether or not it's for debugging, profiling, or sanitizing your code here. We all use them at some point, and they will be working on confidential computing mode. Now you'll see here is that when we actually have confidential computing modes, we will have 3 checkboxes or 3 modes that you can end up using. CC mode off, which is basically a standard H100. Now CC on is where everything is encrypted and authenticated, all the firewalls are up, and therefore truly only the encrypted and authenticated data can go across the bus. We don't give anyone access to things where they might be able to derive some sort of information, like the performance counters. Without the performance counters, a lot of the debug and profiling features of the dev tools are choked out and unable to be used. So as such, we do have this third mode, CC dev tools, in which all the code is still encrypted and authenticated. However, we drop the firewalls such that the tools can access these counters and you can start to get the data you need back to identify things like bottlenecks in your design. Again, we would not recommend going to production with DevTools mode on, as that is opening up a gap specifically to get some extra data about how your application is working. So of course, when you go to run mission mode, we recommend CC mode on. Coming into the libraries here, of course, the big question is always, what will happen to my stacks? What will happen to my libraries? We, again, like I said before, have been working very hard to ensure that the libraries and the software stacks all work without any transition needed by you when using these particular features. So by the time we go to launch here, we will have all of these working in confidential compute mode. CUDA being one of the more advanced ones with a lot of very specific features that did rely on host pinned memory to operate at its full potential, is now creating alternate code paths such that it will work in confidential compute mode. So in summary, what we have here is the early access of confidential compute. We're really excited about it here. This will be coming in CUDA 12.2 Update 1, which should be out in the next few weeks. This, again, will have the support for a single GPU pass through to your virtual machine. The multi-GPU with NVLink will be part of our roadmap, and stay tuned to watch for that. This will support, of course, the H100 PCIe and the HGX SKUs. It will work with both the AMD SEV SMP and Intel TDX CPUs. And of course, we will have both those modes of CC on and DevTools mode on. And during the early access, the systems tracing tools will be the supported DevTools in the early access again. And one of the big things that we're really excited for you to see and get some feedback on, please feel free to file issues once it's up here, is our GitHub. We're announcing an NV Trust repository here, where you're going to start to see the quick start guide, how to get the system set up, all the way from powering on the box as soon as you pulled it out of the off the dry dock, getting the BIOS configured, getting the host up, getting the virtualization software installed, and the virtual machine running, all the way to making it so you can see every step of the way how to get this GPU running and into a confidential mode that you can trust. As I mentioned just previously on the slide, our AI ML frameworks, as well as our libraries, run without changes. So feel free to grab into PyTorch, TensorFlow, TensorRT, start running some of those classic networks, ResNet 50, some of the BERTs. With this bullet here, there will be some CPU side encryption performance impacts, mainly because we have to encrypt using CPU code. That limits the amount of data that we can do at any given time. The faster your cores are, the more cores you have, the better it is. And that's why during the early access, you'll be able to start to do some of these benchmarks and see. If you batch your files or have single large transfers and then more compute and less data transfer, you will notice hardly any effects. The more small transfers you have, that is where you have to encrypt more payloads, and that is where you'll start to see more of the overhead here. And then once we do this, the big question, of course, is when we will move to the GA release. We are finishing our performance tuning. We are doing security soak time, reviews, audits, and of course, we are waiting for not just ours, but of course, Intel, AMD, KVM. Everyone is pushing upstream very rapidly patches into the mainstream Linux kernel, such that it becomes more standardized for a flow here. With that, we'll have 12.2 Update 1 coming out here, and that will have the 535 TRD2 for the driver, and you'll be able to go ahead and just download it off the main website. There's nothing new that you would need to do, no extra flags, no different downloads. If you have a Hopper H100, you do not need a different SKU. This is going to be, like I said, for the masses, and we are doubling down on ensuring our roadmap going forward is constantly being aware of the confidential compute roadmap. All right, I've got one more section here. This is the compatibility updates for CUDA. In 12.2, we don't have too much new, but I like to make sure everyone's aware of it. There is one main thing that I want to bring attention to in terms of an end of life of one of our big long-term drivers. So with this, let's go into, again, the quick review of the 3 compatibility modes of CUDA. I have another YouTube video describing these in much more detail, so feel free to take a look at that on our developer page again. Of course, we have backwards compatibility, meaning our drivers are going to acknowledge code that had been compiled in the past into the future. Forwards compatibility is one where you have installed a kernel mode driver, the KO file, and you do not want to continually update that kernel driver, but you still want to use the latest features of CUDA and the user mode driver. So with that, we have provided packages for our big drivers to come through and let you, for example, install 12.2 and still be able to count on the 12.0 kernel mode driver and have a fairly transparent experience. Minor version compatibility, of course, with the 12.0 series allows your applications that have been compiled to link into the libcuda.so without needing to have an awareness as to whether or not it is on 12.2 code running on a 12.0 driver or 12.0 code running on a 12.2 driver. We do have some best practices and some restrictions that are documented online on our compatibility web pages, as well as on that YouTube video I mentioned before. Just a quick block diagram going over what these are. Again, backwards compatibility, you could say you have an application, let's say on CUDA 7.0, and that's going to be running on the drivers of the future. Forwards compatibility will, of course, replace that user mode driver APIs such that they will be able to access and understand the code that you're using today on older kernel mode drivers. And of course, minor version compatibility, where you might not know the exact driver set installed in your system, and that's okay as long as it's all within a single major version. And finally, like I said, there is some news regarding the drivers and the compatibility that they have. The support of one of our drivers, R450, is receiving its last update with the release of 12.2. That'll be its 13th incarnation with TRD 13. That was one of our LTS drivers, long-term support, which we generally keep supported and patched for 3 years. Our production drivers we release more often, and those will be supported and patched quarterly for 1 year. And of course, we have the new feature branches, which will have the kind of urgent bug fixes or cutting-edge features that will also, be paired with a toolkit when we release it. So the current in-cycle drivers, you'll have 535, which is our new LTS driver that is paired with 12.2, and that will remain in support until summer of 2026. R470 is another LTS driver, which is still in support. That'll go until summer of next year. And 525, which was released with 12.0, that will remain in support as a production driver until the end of the year. So again, if you're using R450 today, perhaps in that forward compatibility mode where you were using, let's say, CUDA 12.0 with 450 as a kernel driver, just be aware you need to start migrating your stuff off and perhaps move to one of our newest, the 535 LTS drivers. If you have any questions, my name is Rob Nertney, rnertney@nvidia.com, and I look forward to providing more updates as the confidential compute roadmap continues to mature. And I hope you all have an excellent day and happy coding.
Hello, everyone. My name is Aarti Sundaram. I'm here to give compiler updates for CUDA 12.2. It's perhaps already familiar. We discussed this, we talked about this in the CUDA 12.0 webinar, and we also made a dedicated technical deep dive presentation if you're interested. But this is just a recap because this has been a big change for us in terms of what we supported in the CUDA 11.x timeframe and what we changed in CUDA 12. And we wanted everybody to kind of be aware, and in case you're moving from 11.x into 12.2 directly, just wanted to bring this up. So JIT LTO, it was a feature that we previewed in the 11.x timeframe, and based on the feedback and the lessons learned, we realized the feature that was originally introduced as a driver API is not fitting into a lot of the compatibility promises and guarantees CUDA does provide. And so we reintroduced it as a CUDA Toolkit feature called using the new library called NVJIT library. So this is a big call to action. So in case you're moving your JIT LTO, if you've already been using it with driver APIs, just want to let you know that those APIs are deprecated. Your application will continue to work, but you'll have to recompile for CUDA 12.0. So flashback, what is JIT LTO? If you have CUDA kernels and you wanted the best performance optimizations, you'll have to put all the you had to you compile it in whole program compilation, which essentially meant all the CUDA kernels had to be in a single file, right? That's when the compiler has visibility to do all the symbols, all the functions, so it can inline and optimize across function boundaries more effectively. So you get the best or the most optimal optimizations when the compiler is having full view visibility. Obviously, that is a big trade-off for general purpose programming, especially if you're moving from a place where you have multiple source files and you're trying to accelerate, and you don't want to kind of, clobber your class hierarchies and move all your functions that has to be now CUDA accelerated into a single file just for performance. So separate compilation allowed you to kind of keep those hierarchical file organizations, multiple source files. You're able to compile CUDA kernels across those files. But then the compiler which performs optimization doesn't have visibility into files outside of its translation unit, essentially one source file. So that's where deferring optimization to link time gives a big boost to performance, because now the linker, which is linking across all these source files, has better visibility and is able to do make the best choices for optimizations without being constrained by file boundaries. So JIT LTO is basically taking the same concept, but if the linking is happening at runtime, for example, if you're using NVRTC and you're linking at runtime, or you're shipping your kernel and then the linking is happening at runtime, in those scenarios, the offline LTO did not kind of help, so we introduced JIT LTO as a preview in 11.x timeframe. But as a device you'll have to use driver API, link APIs with the JIT LTO option for that. And of course, with JIT LTO, you're no longer constrained by the files. So you can have device codes spanning across multiple source files. You can have library codes invoking user callbacks, and you can get the best performance on all these scenarios because now the linker is performing the optimization. And this we kind of achieve not just by deferring the optimization to link time, it also there's another aspect to it, which is instead of for the linker to actually do the optimization, it needs the best source information, like as much source information, as needed. Like it's very easy for the compiler to do the optimization because it obviously has the high-level programming language, but typically, if you're shipping SAS or PTEX, the linker cannot perform such optimization. So we had to introduce a new intermediary. It's called LTOIR. It's kind of a wrapper around the LLVM IR or NVVM, like the NVIDIA version of LLVM IR, NVVM IR. So kind of a wrapper around that. This provided the high-level abstraction that the linker needs for making those optimizations. Basically, the workload B you ship, instead of PTEX SAS, you're shipping these LTOIR fragments, and then if you're using NVRTC, generate these LTOIR fragments, and then the linker can perform these optimizations. So that's the two steps. So it's the high-level abstraction and also deferring the optimization to a later stage. So this the obviously benefit is, as I just spoke, you can have multiple files where you have device codes, and you can also make callbacks across user and library codes, and all this you just generally get the meaningful performance benefits that you would expect from the optimized kernels. But there is another interesting aspect that could be leveraged, right? Because you are able to ship these higher abstractions that can be jittered, so you don't have to ship fully formed kernels. You can actually decompose your kernels and ship into these partial LTOIR fragments, even across modules and even across user and library codes, and then combine them and JIT them into a final kernel on the fly. So when you're able to generate a full formed kernel on the fly, you have the benefits of making the right configuration choices, taking user input into account, and all those benefits. Like, for example, let's say you have gem optimization and you are let's say there's a pre-processing that needs to be done. Like, for example, like you call into user code for loading the data into the memory, and then your library is performing some gem optimization. And the post-processing is basically storing the data back, right? It's very common thing that everybody would have run into. In such scenarios, the user code would have shipped as a SAS or PTEX, and there's no way to inline, and there's just very high perf penalty for the back and forth. Now with this, the user code is LTOIR and your library code is also LTOIR, and you don't have to figure out like what target configuration or what is the gem dimension of your matrix. Also, all that can be computed on the fly, and a fully formed kernel can be jitted. So that means you're kind of reducing the complexity of the your binary essentially, and also kind of reducing the binary size. So instead of shipping like fully formed kernel for all different matrix dimensions, or like whatever target configuration is, instead of all that, you just ship the building blocks and then you figure it out on the fly, right? So this is like kind of leverage of JIT LTO. Obviously, there's some things to keep in mind. As anything, you're shipping an unoptimized kernel. So obviously, in pure terms, those unoptimized kernels are going to be much larger than if you'd shipped SAS or PTEX. But then the good thing is you can actually have these, like funky way of decomposing those kernels, and then you're only shipping instead of shipping like all various different combinations, you may be having a combinatorial explosion in terms of binaries that you're shipping for every target user configuration, you're kind of maybe reducing the complexity that way. But then in pure terms, each kernels might be actually larger. Each binaries might be larger if if you don't benefit really from decomposition. Obviously, much of what JIT-LTO does is happening at runtime. So, like the more complex optimizations that happen at runtime and jitting that happens at runtime, it's all adding to your application runtime performance, right? So obviously that's something you probably know and just wanted to bring it up. Another thing that might be kind of counterintuitive is LTOAR. The JIT-LTO, the LTOAR that we ship is actually not a target computer GPU aware, but then it cannot be jittered to a PTEX for a future architecture. So in case you want to ship your application with LTOAR, you also have to ship PTEX along with it because of that quirk. We are still trying to kind of remove that and enable forward compatibility for a future GPU architecture, but that's not there yet. So until then, you'll have to ship both LTOAR and PTEX. The last thing that one has to remember is LTOAR itself is only compatible within a major CUDA architecture family. So it's only, by which I mean the Toolkit version. So if you're shipping your application, if you have like mixed binaries across different toolkits, you'll want to ensure that you are linking to the right NVIDIA link toolkit library. So you'll want the highest version for each major family. Like for example, if you have like for CUDA 12 and CUDA 13, they're not compatible. So you cannot use an NVIDIA link from 12 for a CUDA for LTOAR generated from a CUDA 13 or future any other major family toolkit. So that's primarily what JIT-LTO is, and it's hopefully if you're on 11.x, you can migrate to the 12.x version of JIT-LTO using the NVIDIA link APIs. These APIs are well documented in the CUDA documentation. And there's also, as I mentioned, there's a YouTube webinar, and our compiler senior engineer, Mike Murphy, has given, and along with me, we have a detailed demo, and we also speak to the finer nitty-gritties on how the versioning actually works. That I think is slightly something to keep in mind, right? So please try it out and let us know let us know your feedback and your use cases, and how, if you found something else that's interesting, how you leveraged JIT-LTO for your application. So the next big ticket item falls into the umbrella of reentrancy. This is a big topic for us because it's something that's been asked so many times from all. This is an area that we've been constantly being asked to improve, which is compilation time. Both offline compilation time if you're using NVCC, and on runtime compilation time if you're using NVRTC. So there is an aspect of a compilation workflow that we have improved, which is the NVVM reentrancy. So this is NVVM is our optimizer. So if you you just heard me say that in the context of LTOAR, this is the same piece that does the link time optimization. So this optimizer is now more reentrant. So we are trying to eliminate all those deep mutexes from our call paths as much as possible. So there's two aspects to NVVM reentrancy. One is how we have improved, how it could be improving single compilations, by which you have like an NVCC or a single NVRTC invocation, and then how do you improve the compilation for that, improve the compilation time. So we have something called split compilation. You'll have to pass in -- split - compile, and then a number n. With NVCC or NVRTC, this option would work. Basically, what it does is our optimization actually happens at the kernel device function boundary. So if you have like a non-inlined, if you have multiple kernels and they're not getting inlined, so so to speak, there is inherent parallelization that is possible with like the optimization. So each of those kernels can be parallelly optimized. So then we can do that. Now you have to specify how many kernels you'll have to use this way. Like largely, we don't want to end up oversubscribing the system with too many threads. So that's a possibility. So you can pass the number of threads we can use to parallelize the optimization phase in our compilation flow. This is applicable, as I said, for both NVCC and NVRTC. One caveat to keep in mind is if you're using -T, we spoke about this a lot in 11.x timeframe. -T allows NVCC to kind of, if you're compiling to multiple target architectures, so those compilations can be parallelized with with number of threads that you pass in -T. If you're using that and also you're adding split compilation, then it's probably you're going to be in because of the multiplicative effect, you might be oversubscribing the system. So you'll want to use caution in how you want to kind of use parallelize. This is mostly dependent. It isn't like a magic sauce of number. It mostly depends on how your code is organized and what kind of optimizations and how much overhead each entails. So you'll want to kind of figure it out by trial and error. And then the last part is, this is something I want to kind of preface it by saying, please use this, what I'm going to say, this new feature, this next feature I'm talking about is an experimental feature. So as I mentioned, JIT-LTO, when we introduced it, it was kind of, we call it preview, but I think the definition may be kind of unclear. So when we say preview or experimental feature, it is really use it with caution. We might, if we're just sharing that out because it gives us an opportunity to kind of get this early to you and also get feedback, and you get to try it out without waiting for us to kind of finally formalize this. And also there's never really a good way to model all sorts of way CUDA gets used. Even like within NVIDIA, we have like large base of CUDA users. It's just interesting the way, kind of different ways in which CUDA gets used. Obviously, everybody wants the best performance, best compilation time, but they're always like kind of trade-offs. So we cannot obviously model all these trade-offs internally. So that's why it's a way for us to kind of get things out early and get early feedback. So that's there. But then we, as part of the early feedback, as part of the whole feedback process is to correct ourselves, right? So when the feedback is, not so good, we might have to go back to the drawing board, and then it doesn't make sense for us to sustain a bad design, right? So we might pull things out. Also, like if you're using this in production scenarios, so you might want to like be careful, because obviously we test them, and these are not like, copy work that we are laying it out, but in general, there might be situations where it doesn't work well. So use caution when we say experimental or preview feature. So this feature, which is specifically targeting multiple NVRTC invocations, because this is an area where we've gotten like kind of a lot of feedback from external users that they want to kind of speed up the runtime compilation, especially because it adds to the application runtime overhead. And then when that happens, they're not really seeing the benefit of parallel invocations, because we had these, NVVM optimizer was not really re-entrant, and we had these deep mutrixes. We are trying to kind of remove all that, but with caution. So these things can potentially have like latent effect. So that's the big caveat. Once I'm done with my preamble, so the feature is basically allowing NVVM optimizer to now be parallel, right? So if you have like multiple NVRTC invocations, as you can see at the top, before the NVVM optimizer cannot be in parallel. So the first NVVM, if there's already an NVVM optimization phase kicked off from one thread, the next thread is basically waiting for that to complete. Now with that mutex gone, and you can really get parallel invocations. So NVVM and from multiple threads can go in parallel. So this is already the case for the code gen phase. So the ptext to SAS, if you're compiling, that is already parallel, but the NVVM was serialized. But keep in mind, the parser phase is still serial. So if you have like a large header file, and you're kind of your big bottleneck is parsing the header file. And if you know that from your CPU compilation efforts as well, that is your bottleneck, this is still going to be the bottleneck because the parser is still serial. But if it's not, if parser is not a bottleneck and a lot of the compilation time was spent on NVVM optimization phase, then you should see performance, the compilation time should improve. So in order to enable this feature, you will need to set this environment variable, which is an internal environment variable. It might go away anytime. So as I said, please use with caution. So nvrtc underscore internal underscore concurrent underscore NVVM equal to 1. So you'll have to use the set this environment variable before loading the library, and then you should see the parallelization benefit. One other point I wanted to make is if you're compiling, do compile to Cubin instead of compiling to PTEX and then JITting, because you now get the benefit of full concurrency through to the code gen phase. So those are the big ticket items. So try out JIT LTO, try out concurrent NVVM optimization using split compilation. Also check out how parallel NVRTC invocations are performing for your application. Obviously, all this will kind of depend on your work on your application and what kind of work it is doing. And so, we are very eager to get your feedback. You could reach out to us. There's a developer forum. You can provide a feedback there. So we'll look forward to that. Thank you.
All right. Thank you so much for joining us today. We hope you've learned a lot about all the great new stuff we've got in CUDA 12.2. We've got some links on the screen here. I'll put the links in the chat box below if you're looking for further information or further details on anything we've shared. Also, do check out our blog posts. We've got some blog posts coming out very soon on HMM with some more detail there and some of the other general features that are coming out in CUDA Toolkit 12.2 and beyond. With that, thank you for coming today. My colleagues and I have enjoyed being online live, the live Q&A and chat, and we're looking forward to seeing you again soon. Thank you so much.